Swayam Prabha. Digital India. Educated India.
Hello and welcome to the next part of the tutorial. So in the previous class we have learned about this delta method, like aerodynamic parameter estimation using delta methods, where I have talked about the architecture adopted by delta method, which was feed-forward neural network, and you also got to learn how neural network works and how it is being trained, and then you could, like how to use further delta method. So just I'll quickly revise like what we learned in the previous class. So as I said, like it mimics our biological neurons. So if you see the architecture of single neurons, it was like this. So it had some bias inputs with certain weightage, right? So this is your bias, and you can have a different inputs x1, x2, x3, and there you need to sum all those, and then it should pass through a nonlinear activation function. Nonlinear activation function. And it could be your any kind of sigmoidal function, 10 sigmoidal, logarithmic sigmoidal, or it can also be a linear, simple linear function. Right? So this figure talks about your artificial neuron. I should write here. Artificial. So this is the architecture of your single neuron. This whole thing is a single neuron. Yeah. So you have the inputs and associated weights also will be there, W1, W2, W3, and bias, let us say B, and then you have to sum all the effects, and then you have to pass through nonlinear activation function. Then you will get here as output, right? So what we did, like all the solution now depends on the complexity of the problem. So every kind of nonlinearity can be captured by using a suitable nonlinear activation function. So that's why ANN is also called universal approximator, which can approximate any kind of nonlinearity. The activation function which we discussed was let us say f of y, and it is 1 minus lambda y divided by 1 plus e to the power minus lambda y. And here now you can see here you can also modify this nonlinear activation function with the lambda parameter, means you have the control on the function with this parameter. So this is called, lambda is called gain of activation function. So here you have the flexibility of selecting this activation function. So this is basically 10 sigmoids. Okay. And then with that activation function, once you got this output from the neuron, so now it will propagate to the next neuron if it had some other layers, right? So that is how we understood. And then getting the neural network model is about assigning a appropriate weightage or right weightage and bias. So with that you can have a defined neural network model, right? And the learning of this model can be done using this back propagation algorithm, which we have discussed earlier. So it is based on steepest descent method. So if you see this back propagation algorithm, which is based on your steepest descent method. There you saw how the updation of weight is done. So it was basically your W of, suppose you want to update weight like this. So it is K plus 1 is instant weight was okay WK, or here it depends on like how you are selecting your error function. So you can also like this, or dou or dE by dW, right, this weight. And then suppose your error is becoming constant for some reason, then to improve that you can add this momentum parameter with Wk minus W of K minus 1 W of K minus 1 one step back again. Yeah. So this is learning parameter. So it decides your convergence of output, and this is momentum, which improves the result. Momentum parameter. When it is used, when your error versus, suppose in this case here it is constant. So in this case your dW by dE by dW term, gradient term will be 0, so that in that case it will alone it will not be able to update, so that you need additional term of momentum parameter where you will get the updated weightage. Yeah. So this is what we learned, and once you have the trained network with the help of your input and an output, let us say these are your input and output. So in our example, we'll make it CL, CM as output, and then alpha, delta E, QC by 2. These are our input. Right? These are our input. This is output. Now you got this model which was earlier black box. You got this model which was earlier black box as feed-forward neural network based model. You got a trained model. Okay. So this part we have done now. So for the delta method, what it suggests, like you now start perturbing the input. So suppose if I want to find CL alpha, then you perturb alpha in both the directions. So corresponding to that, you will see the responses in CL. Like suppose for positive perturbation it is CL plus, and for negative perturbation it is CL minus. Then twice of the perturbation actually in both the directions. So you will get CL alpha like this. So other variables also like CL delta E, CM delta E. If you perturb delta E by delta E, then you will see the changes in force and moment coefficients. You can write like this, and you will get that. So now the whole heart of this method is about getting this model, FFNN based model, feed-forward based neural network model. So just to make it simple, you can also use this toolbox which is available in MATLAB software. So just I will demonstrate in a simplistic way, so that you can actually model this once you have the flight data available with in the form of alpha, delta, EQC by 2B and CL and CM. Then I'll tell you how to design this network model, and then you can use this method to estimate your parameters like CL alpha, what I discussed. So and then later I'll just explain you, or I'll demonstrate with the help of HANSA 3 data, which I said like I'll be talking about the examples with HANSA 3 flight test data, how to estimate the parameters. Then you can see the results, and then you can also try some of the different flight data to estimate the parameters on the after the learning this method. Okay, so I'll start showing you the NN toolbox. So we'll learn NN toolbox in this session and then with example. So as you can see in the screen, this is a MATLAB software of 2014A version, right? And this window is called command window. Most of you may be knowing it. So as I said, in this section, we will be talking about this NN tool, right? NN toolbox. So now in hand you have the data which I have written x in hansa3.mat file, mat file, z output underscore hansa3. This is the output data for your problem. So here now we are ready with the data, input data and output data. So x in is input data, x out, z output is your output data. So first of all you can load this data. So once you load this data, so here in the workspace you will see it is like x in input data. Just drag and drop in command window, you can see the data is loaded, right? And further information you can see if you expand it, you can see all the information. So essentially x in is your free cross 796, z output is your 2 cross 796. So what it says, it means you have 3 input data of 796 samples, 2 output data 796 samples. So these are your corresponding minimum and maximum values in the rows, and this is for your output. Now I'll be showing you about NN toolbox. So just you write NN tool here, and if you press enter, then you'll be able to see this toolbox. Yes, okay. So here what you can see, here you have the box for input data, and this is for target data, which is our output data. And here you can see it is a network. So I'll just tell you how to design a network, feed forward neural network using input data and output data. So let us start loading the data. So you can load the data using this import. So basically we are trying to import the data. So input data is our x in. So please select x in here, import. So here it's coming like variable x in has been imported as input data into the network or data manager. It means we have imported the data. Now target data is our output data. Select the output data. Now you can import your output data. Yes, so now you can close this. Now you are able to see in input data box you have input data, target data box you have output data. Next thing is now to design a network, right? So you select a new network where you can keep the name of your own. So I'll write network underscore Hansa 3, right? So you can write Hansa 3. So if you are going to design a Hansa 3 network, or example is about longitudinal, so you can write LON. So now we are trying to create a network for Hansa 3 longitudinal data, right? Now you see the network types. Already we have discussed about feed forward network. Training is done by back propagation. So this is the structure, default structure. So you can select that, or you can also try with some of the different methods which is up to your interest. Like if you want to go further, you can go for other things. So this is your feed forward back propagation network type. Input data already you have loaded, so you make it x in, target data z out. So training algorithm, I'm using the default. You just for a starting purpose, for beginning, you can use most of the command, most of the data which is already been assigned here, default data. And as I said, this number of layers talk about hidden layers, number of hidden layers. So you can take one, because one hidden layer is good enough to capture the complexity of such kind of problem. So this is the layer number 1. Now in this number of neurons, so you have now command over or control over number of neurons in hidden layer as I said, number of neurons in the input layer is number of inputs whatever you have. So since we have 3 inputs, so default we have 3 neurons in input layer, and we have 2 outputs, CL and CM. So we have 2 output 3 neurons in output layer, but this number of neurons is about your number of neurons in hidden layer. So default it is coming 10. So if you want to change it, you can change. You can take whichever number you want. So as I said, like it's good to start with the default values. Let's see what happens, and then this is your transfer function, activation function. So as I said, activation function can be of different types. So default is tan signum function, right? So just take this tan sigmoidal function, and now you can create your network with these values or the variables. So create a network by clicking on create. Okay, so now your new network called network underscore Hansa 3 underscore launch added to data manager since you were able to create your network, right? Okay, if you want to view your network, you can see from here. So this is what is your network look like, right? So here you have 3 inputs. So number of neurons are 3 in input layer. Number of neurons in hidden layers you have selected 10, so it is 10. Output layer you have 2 neurons, so it is 2 neurons. Okay, so now you can close this. So you have your network structure ready, right? So if you want to save, you click on it. So this is your network straightforward neural network model. Now you want to train your network, right? So go to training and train here. So these are about the training data. So we have to fit input is about xn and target data is your z out. The rest of the things you don't have to do anything. Now here you can see different tabs are there. So you can explore more with your own. So let's do it with default data. So just I'll train network using those data. So now you see your network got trained and it converged in 62 iteration. Number of iterations you can see here. These are the information related to performance time. And if you want to check your performance, you can see it from here, right? So let's see. So this y-axis here talks about mean squared error in training data, validation data, and test data. And this dotted line talks to you about the best result where your validation error came minimum for the first time, right here. So ideally your network will stop here. Training should be done till this, but it has taken 6 more values as per this augmentation of this feature here. So blue line is about your training error in training data. Green is about error in your validation data, and red is about error in your test data, and dotted line is about best performance. So with number of iterations is called the epoch, your error is drastically changing. It is reducing to a very low value, even lower than your 10 to the power minus 4, and first time your validation error come minimum at this number, maybe around 56, this value before this 62, and here your network is trained very well. Here how it works, like you use 70% of the data for the training, the rest of the among rich data 15% for validation and 15% for the testing of your results. The validation makes sure that you have not done the overfitting. So that's why 15% of the data which were not included in the training were used to check it is not overfitted. Okay, close this, and now you can see the regression where you will get the confidence in your result like this. Yeah? So here you can see 4 different boxes. First is your training, validation, test, and this is about including everything, all the results. Okay. So now you see this how well they are fitting, and the information of this fit you can get from this parameter R. So basically you understand like this: R, when R is 1, it means all the data samples are fitting on single line, the best fit line, right? So R talks you about the relationship between the fit data and from the observed data. So these bubbles are data, this for the best fit, right? So here fit R value is quite high, almost close to 1. So that's the reason you can see all your data samples are able to fit on this blue line, best fit, for the training. Validation also you got very good result, 0.9997, almost all the data samples. So as you know, we have used total 796 samples. So all the samples, almost all the samples, including few, maybe 5, 6, are slightly out of this line, but reasonably good. So that's why you did not get R equals to 1. But validation, R value validation shows it has got a good training. And then you have tested with different data, and then this also says you about confidence in the trained model with a very high accuracy of 0.997. So it could also be here, you will get the result together. Yeah. So it means now you are able to train your model with this training, and then suppose it doesn't converge in first time, you can try doing multiple times, and then you can also now see the information about the weights and bias which I talked in theoretical explanation part. So you see that associated weights are here and including bias. And if you want to change the weights and bias, you want to include your own weights, you can do it independently. You can do it. So here idea is like you can explore the different features of this toolbox, and then accordingly suitably you can modify as per your result, right? As per your requirement. Now again you are able to create this network model. You can export it to your MATLAB file. So this network underscore 3 underscore learn is about training of the network. You can export, or you can also save this. So okay, so yes, this is now saved. Other information also, information on the error, you can also check and see. Okay. So now you got this network model. So how will you test? Like suppose if you have different data, so for that you can write predicted output. It works like this. Just I'll write you the command, and then you can do it by your own simulation of. Since the network name is Hansa3, this one, so you have to write this. Just you can copy and paste it. Okay. You write this name. And here you can give your different input, right? So here I have trained this network using this input output data. So just to show you, I have shown only input output data. Suppose now you got different data from different flights, different set of flight data. Yeah. So it may be X2 or something. So if you do it, you can write that. Since we don't have data available, not sure. So if you have you have tagged the name like X in 2, you can write X in 2. So here I have, suppose you want to just see the result for the same data, you can write X in here, right? So it will give you the result for predicted output. So now you see, you got again 796 samples of data for both the outputs, CL and CM, right? Here. So this is just basically predicted. So once you have designed your network like this, then you will be able to predict the output for any inputs which is suitable to this model. right? And then once you got this predicted output like this, so what essentially you want to do now, you want to perturb the inputs, x, let us say x in, it contains your input information about alpha, delta E and QC by 2V. So you can give different inputs, so you can add first time maybe difference in alpha, you note down the values, like you save it somewhere, again you perturbed in the negative direction, maybe x in minus delta alpha, you keep some different name with different variables, store it, and then finally from the delta method, if you want to find CL alpha, then it will become your predicted output for the positive perturbation minus predicted output for the negative perturbation divided by twice of the perturbed input will give you the corresponding CL parameter. So this is what actually we have done it, and I'll show you the result. So this was the part of the process and demonstration of an toolbar. So I hope you will be able to appreciate, and then you can also do it by yourself. So let us see aerodynamic parameter estimation using delta method. So basically we have taken the same data what we have used for least square estimation demonstration using ANSA database. So this is the aircraft which you have seen already in earlier tutorial session with the parameters, and this was your flight data which you are familiar now. And if you see the input and output, so it was like this. So this is alpha QC by 2V delta E, CL and CM. So what essentially you are seeing here, you have set of input data, set of output data, and this is the model actually. So this is your aircraft ANSA 3, where you are no more worried about physics of ANSA 3 aircraft, physics of this aircraft. Now you are treating this as a black box model. You have gathered the data from flight in terms of input, sets of input and set of output data, and you are trying to replicate this model using the philosophy of artificial neural network, which is a very powerful method. As I said, it can approximate any nonlinearity, and once you have trained this model, like you have this now trained model of ANSA 3 longitudinal data, then here you can see blue line says about the training data, the data used for the training, and the red line shows about ANN estimated. What we did, like we had trained this from the first flight data set, different flight data sets, and we have used different flight data set input to estimate the coefficients CL and CM, like force and moment coefficient. So they are reasonably well, like matching with each other, and then like once you apply your delta method, I hope you are able to see this. So this is your result for all the parameters. So the parameters are here: CL alpha, CLQ, CL delta E, CM alpha, CMQ and CM delta E. So this is a histogram plot with histogram information. So histogram, what it says, like it says you had multiple data samples, like around 796 samples. So this gives you the information about maximum occurrence of particular value from all the sample data. For example, if you see CL alpha plot, if you see here CL alpha in CL alpha estimates, so it is close to 5, between 5 and 6, so let us say 5.5. so the occurrence of that value happened more than around 350 times, right? And this value also is quite prominent, the next value. Like that you can see all the estimates, occurrence of all those estimated parametric values for how many times it occurred, and you can also take the average value, you can also select the maximum number of occurred values which will represent your corresponding your aerodynamic parameters, right? So here it was about CL and CM derivatives. You can see all the results are here, and now if you compare this with your results what you have got earlier using least square method, so these are the results presented here. delta method estimates for longitudinal parameters using ANSA 3 aircraft flight data. Okay, so you see here you have CL alpha, CLQ, CL delta E, CM alpha, CMQ and CM delta E. Estimated parameters using delta methods and using least square methods. If you see, they are reasonably in the agreement. CL alpha 5.788 you got from the delta methods, and then 5.411 you got from the least square methods. Here your strong parameters are CL alpha, CM alpha, CM delta E and CL delta E. So those strong parameters are in quite good shape, and then you have done it from flight data. Further, this thing you can improve, you can apply for the different sets of data, you can see the accuracy in the result and performance. And as I said, Q derivatives, CLQ and CNQ were not very much in agreement because of the nature of the data. So maybe you can design a better input. Here we have applied only 3 to 1 1. So if you want to get those dynamic derivatives, then you should capture the more dynamic maneuvers, nonlinear maneuvers, where your Q will be quite excited, where you will see the significant changes in this rate derivative, and from there you can get better estimates of CLQ and CLQ. So this was the idea of just to introduce you with this delta method using flight data. Now you can gather different sets of data, you can use this algorithm, and you can look for a better result what is being presented here. I think it should be good enough to understand you and to start for new flight data sets. So I talked about the procedure, like how do you design this network, and then from the network, by using philosophy of delta method, how to estimate the parameters. So I think this is all for this session. You can practice more, you can come up with your own ideas and methods, and you can see the comparison of your results. Thank you so much.